So when you look at your very first protocol buffer file,
Yeah.
right, you see this line, string name equals 1.
Right.
And your programmer brain just immediately tells you, oh, that is a default value.
Which is totally understandable, but it's not.
It is not.
Yeah.
Everything you think you know about field assignment is just wrong here.
Uh-huh.
That number 1 is actually a wire identity tag.
Yeah, the field name itself, like the actual word name, it never even appears in the serialized bytes.
Which is wild to think about.
It is. I mean, you write it in the file for human readability, obviously, but on the network, that data is identified exclusively by the number 1. And, this single design decision is the core reason why Protobuf messages are just a fraction of the size of JSON payloads.
Welcome back to the deep dive, everyone. You are a software engineer. You probably spend your days jumping between Python and Java, and you already know the architectural pain points of scaling JSON across microservices.
Oh, absolutely. The lack of a strict schema, the massive verbosity of sending those same field names over and over as strings.
Right, and just the heavy text parsing overhead on the CPU. So from our last dive into Chapter 1 of our series, Protocol Buffers for any software engineer, you understand the overarching concept of a .proto file acting as a single source of truth.
The master contract, basically.
Exactly. So today it is March 2026, and we are unpacking Chapter 2. Our mission today is to actually write that very first contract file.
Yeah, we're moving from the abstract theory of, why we need a formal shape for our data into the actual physical syntax of defining that shape.
And that transition requires a really fundamental shift in how you think about variables in memory.
It really does.
But that shift starts before we even define a single piece of data.
Right.
We have to build the foundation of the file first, establish the rules of the environment we're working in.
Right. Every proto file must start with one specific line. Its syntax equals, quote, proto3, unquote.
And that has to be the very first non-comment, non-empty line in the entire file.
No exception.
So the best analogy I could think of for your day-to-day workflow is comparing it to a Java file, starting with the package statement.
Oh, that's a good way to look at it.
Yeah, because it doesn't do any active data processing, right? It simply sets the namespace and the ground rules for absolutely everything that follows it.
Exactly. And the compiler enforces that placement strictly, mostly because of what happens if you actually omit it.
Right, what does happen?
Well, if you forget the syntax declaration, the protocol buffer compiler just defaults to Proto2.
So it silently falls back to a legacy standard.
Yep.
Why is that such a dangerous trap for a modern application, though? Like, what's so bad about Proto2?
So legacy Proto2 operates under entirely different rules, specifically regarding how it handles the presence or absence of data. Like in Proto2, you had to explicitly label fields as required or optional.
Okay, I mean, on paper, that sounds great.
It does. But in practice, across massive distributed systems, required fields became an absolute nightmare.
Really? How so?
Well, imagine you ever needed to deprecate a required field. You couldn't, because old services that were still expecting that field would just drop the entire message if it was missing.
Oh, wow. So it made schema evolution incredibly brittle.
Unbelievably brittle.
I can see how that turns into a distributed monolith problem. You try to update one microservice, and suddenly you break the parsing logic of a downstream service maintained by a completely different team.
And that was the reality for years at big tech companies. But Proto3 kind of wiped the slate clean. It dropped the required keyword entirely.
Oh, nice.
Yeah, it simplified the rules around default values and just made the whole system far more predictable for modern ATI design. So by explicitly declaring syntax equals Proto3, you are locking the compiler into these modern safe behaviors.
You're just avoiding all those legacy traps right out of the gate.
Exactly.
Okay, so the ground rules are set. The compiler knows we're in the modern era. How do we actually model the data?
Well, this brings us to the core building block of the file, which is the message.
Right. And to map this to your current workflow, you should think of a message directly as a Java class or like a Python data class.
That's spot on. The message is just the fundamental unit of data transfer in protocol buffers.
It's basically just a named collection of typed fields enclosed in curly braces. You write the keyword message, then the name of your data model, open a curly brace, list your fields, and close it.
And for those coming from C-style languages, there's a fun little quirk.
Oh, right. No semicolon.
Yeah, no semicolon after that closing brace, just the brace.
But the real friction point I noticed here for new developers is the strict naming convention.
Oh, yeah, the compiler is highly opinionated about how you name things in this contract.
The rule basically dictates that messages must use CamelCase, so starting with an uppercase letter, like capital U user.
Right.
But the fields inside that message must use snake case, all lowercase, separated by underscores. So full underscore name, not full name with a capital N.
Yep, that's the standard.
But like if I'm a Java developer, my muscle memory is going to fiercely fight that snake case rule on the fields.
Oh, for sure.
Why not just write it in CamelCase if my primary backend is Java?
Because you have to remember, the .proto file is not a Java file. It is a language-agnostic polyglot.
Right, okay.
The Protobuf compiler is going to read that single file and generate code in multiple different languages simultaneously.
So it's translating.
Exactly. If you write full underscore name in snake case, the compiler's Java generator is actually smart enough to translate that into idiomatic Java.
Oh, that's clever.
Yeah, so it will automatically create a user class with a getFullName method and a setFullNameBuilder method, properly CamelCase.
Okay, and meanwhile, the Python generator sees the exact same snake case field in the proto file.
And it creates a Python object where you just access user.full_name directly.
Which is perfectly idiomatic for Python.
That's exactly the intent. But if you fight the convention, and force CamelCase onto the fields in the proto file, the compiler's translation logic just breaks down.
What happens then?
You end up with generated Java methods that look like getFullName with a lowercase n, or just bizarrely cased Python properties that fail every linting check in your CI pipeline.
Okay. So you write it the Protobuf way in the contract, and the compiler handles the cultural translation to your target languages.
That's a great way to phrase it, yeah.
Okay, so inside these messages, we have our vocabulary, right? The built-in scalar types. Now, we're not going to insult your intelligence by explaining what a Boolean or a 32-bit integer is.
Right, you use those every day.
But we do need to look at how Protobuf handles them under the hood compared to native languages.
Yeah, so the core numerical types are straightforward. You've got int32 and int64 for integers, float, and double for decimals.
And the distinction between 32-bit and 64-bit is largely just about reserving the necessary memory space in the generated code, right?
Pretty much. Like, a Unix timestamp in nanosecond requires an int64. But a simple product quantity, that's fine in an int32.
Makes sense. But the text handling is where it gets highly specific. The string type in Protobuf is strictly UTF-8 encoded.
Always, always. It is not just a suggestion. It is a hard guarantee built into the contract. Any textual data names, JSON snippets, URLs, that all goes into a string.
But this brings me to a structural question about the language design here.
Okay, what is it?
There's also a completely separate bytes type.
Yes.
Hold on. If strings are essentially just byte arrays under the hood in Java and Python anyway, why clutter the proto syntax with a dedicated bytes type? Why not just put everything in a string and let the engineer handle the casting on the application side?
That is a really critical distinction, and it's based entirely on parser safety.
Okay, parser safety, explain that.
Because a proto string is explicitly guaranteed to be UTF-8 encoded text, the generated code actually relies on that guarantee.
So it trusts you completely.
Exactly. When the Java or Python deserializer reads a string field off the wire, it immediately attempts to decode those underlying bytes into UTF-8 characters.
Oh, I see where this is going. So if I try to shove like an encrypted blob or compressed image payload into a string field,
the parser will attempt to decode that raw binary data as UTF-8 text.
it's going to fail.
Hard. It will encounter invalid byte sequences, and depending on the language implementation, it will either throw a fatal exception and completely crash your service.
Yikes.
Or, even worse, it will silently replace the invalid bytes with replacement characters, permanently corrupting your binary payload.
Oh man, silent data corruption is the absolute worst.
It is. So the bytes type exists as a safety net. It basically tells the compiler, hey, hands off. Do not run this through a text decoder. Just pass this to the application as a raw byte array in Java or a raw bytes object in Python.
That makes perfect sense. It's an explicit instruction to the generated parser about memory safety. So things like cryptographic hashes, file attachments, raw serialized data from another system, those strictly belong in a bytes field.
Exactly. It creates a really clear boundary between human-readable text and machine-level binary.
Okay, so we have the syntax rules, the message structures, the naming conventions, and the types. Let's circle all the way back to the hook that started this whole discussion.
The wire identity tags.
Yes, the numbers at the end of every field declaration.
Right, like string name equals 1.
Because in a normal Python or Java class, renaming a variable is a safe routine refactor, right? You right-click, you hit rename in your IDE, and your whole code base updates. The variable name is the identity.
But here, the field number is the permanent historical identity of the data itself.
And the implications of that, I mean, it cannot be overstated because the number is the sole identifier on the network, right?
Yes, it represents a strict, unbreakable contract between every system that has ever read or will ever read this data.
Wow.
Once you assign a field number to a specific piece of data and deploy it to production, you can never, ever reassign that number to a different field.
Okay, let's play out the disaster scenario then. What actually happens at the database or network level if an engineer decides to reuse a number?
It gets ugly fast.
Like, let's say field number 1 used to be the user's string name. And a year later, they delete the name field, and they assign field number 1 to an integer status underscore code.
The failure is catastrophic precisely because the decoder is entirely blind to the human-readable text.
Right, it doesn't see the word name or status code.
Exactly. Imagine you have a database full of old Protobuf messages stored as binary blobs, or even just a delayed message queue holding payloads from yesterday.
Okay.
The old service serialized the string, quote, Alice, unquote, and tagged it as field number 1.
Right.
Now your new service reads that binary payload. It looks at the contract, sees that field number 1 is supposed to be an integer status code.
Oh, no.
Yeah. It takes the bytes representing the word Alice and blindly attempts to parse them mathematically as a 32-bit integer.
Because it has no idea the original variable name was different. It just sees the tag number.
Exactly. The parser will interpret those text bytes mathematically, resulting in massive, completely nonsensical integer values for your status code.
So you've just silently corrupted your data pipeline?
And by the time you notice the weird analytics data downstream, the damage is already done. Field numbers are permanent wire identifiers.
That fundamentally changes how you approach writing the schema.
Yeah.
Like you are building a permanent append-only log of identities.
Yes, append-only is exactly the right mindset.
Now, this doesn't mean your numbers have to be perfectly sequential forever.
Right.
Right? Like if you delete fields over time, gaps in your numbering are perfectly fine.
Oh, totally fine. You could define a message with fields numbered 1, 2, 5, and 20.
Right. As long as they're unique within that specific message block and they're positive integers, the compiler accepts it.
But that actually raises a performance question.
Okay.
If you can pick any positive integer, and these numbers are the permanent anchor on the wire, is all numbering created equal?
Oh, that's a good point. Could I just start my fields at like number 900?
I mean, you could, but you would be throwing away one of the most elegant network optimizations in the protocol buffer specification.
Okay, I'm intrigued. What is it?
Not the 1 to 15 rule.
So this bridges the gap between abstract software architecture and the physical constraints of network bandwidth. How does the numbering actually impact the bytes?
So every time a field is sent over the network, its identity tag obviously must be sent alongside it, right? Protobuf optimizes this by using variable length integer encoding. Now, we'll dive into the deep bitwise math of that in Chapter 4, but the core concept is simple. Smaller numbers take up less physical space.
Okay, that makes intuitive sense.
If you assign a field a number between 1 and 15, the system can actually pack that field's identity tag and its wire type into a single byte.
Just one byte.
Just one byte. But the moment you assign field number 16...
Takes more space.
Yeah. From 16 up to 2047, the encoding requires 2 bytes just to store the identifier.
Oh, wow. That is a massive architectural hint.
It really is.
So as an engineer, I should explicitly reserve slots 1 through 15 for my most heavily trafficked, frequently populated fields.
It is a highly practical habit. I mean, think about a core event payload that gets sent from your backend to an analytics pipeline millions of times per second.
Right, the volume is insane.
Your core always present data, the user ID, the event timestamp, the primary action code. Those get the VIP slots. Numbers 1 through 15.
So by simply ordering the numbers correctly in a text file, I am basically saving 1 byte per field per message across millions of messages.
Exactly, and that translates to measurable reductions in network egress costs and serialization time.
That's amazing. And meanwhile, the rarely populated fields, the optional metadata, the edge case error strings, those just get relegated to number 16 and above.
Right. For a tiny internal tool, it won't matter. But when you are building at cloud scale, treating slots 1 through 15 as premium real estate is a crucial design pattern.
We have covered a massive amount of architectural ground today. Let's step back and look at the anatomy of the file we've mentally constructed.
Yeah, let's do it.
We're not going to read the punctuation out loud, but just think about the shape of the document, right?
It's remarkably concise when you look at it.
It really is. At the very top, you have your syntax declaration locking in modern rules. Below that, your CamelCase message block acting as the container. Inside that block, a clean list of scalar types and snake case field names.
And anchoring each line is that unique permanent integer acting as the wire identity tag.
What you're looking at is a pure language-agnostic schema. It contains no business logic. It has no dependencies.
It is simply a mathematically strict contract that both the Python service producing the data and the Java service consuming the data agree upon.
Exactly. So to summarize your new toolset from Chapter 2, you now understand why Proto 3 is basically non-negotiable for modern systems.
Right.
You know the exact naming conventions required to let the compiler translate your schema into idiomatic code across different languages.
You know the boundary between UTF-8 strings and raw bytes.
And most importantly, you know that field assignment numbers are not default values. They are permanent wire identifiers, and those first 15 slots are your secret weapon for network performance.
It is a solid, resilient foundation, but, as it exists right now on your hard drive, that .proto file is just a text document.
Right, it defines the shape, but it doesn't actually execute anything.
It's just sitting there, acting as a blueprint.
But it is a loaded spring. In our next deep dive into Chapter 3, we're going to finally unleash the Protobuf compiler on this blueprint.
That's where it gets really fun.
We'll look at how the Protobuf tool actually generates usable Python and Java classes, how the builder pattern emerges in Java, and how those native languages handle the heavy lifting of serialization for you based on this exact contract.
That is the exact moment the abstract schema becomes physical, executable code running in your services.
But before we leave you today, we want to pose a lingering architectural puzzle.
Oh, this is a good one.
We spent a lot of time today emphasizing the strict permanence of field numbers. The rule is absolute. Once a field number is assigned and used in production, you can never reassign that number to a different data type without corrupting your databases or crashing your decoders.
It is a permanent anchor.
But business requirements change constantly. What happens next year when your product manager decides the single-string name field is no longer sufficient and you need to replace it with a first underscore name and last underscore name field?
Happens all the time.
If those wire identity tags are strictly permanent and you can never reassign them, how exactly do you safely evolve your schema over time without breaking downstream consumers?
Think about how you version your standard Python or Java logic today and consider how this permanent binary identity completely changes the rules of backwards compatibility.
We will leave you to mull that over. Until next time.